at this point. Thank you. So it's our pleasure today to have Dr. Vipin Kumar as our seminar speaker. Dr. Kumar is a Regents Professor and holds William Norris Chair in the Department of Computer Science and Engineering at the University of Minnesota. He has a long-standing research interest in data. Applied these to such impactful areas as climate ecosystem and a number of awards and honors. I think one of the ones finished serving as the lead PI of a 5-year project and using a data-driven approach, which was an NSF expeditions in computing. He has had a number of honors. I would ask you to look at his webpage for that. With that and thank you very much for accepting our invitation to give this talk. And let's see if we can share the slide again.
I will share the screen.
Yeah.
All right, so I guess, Desh, thank you for the invitation. I'm happy to be here. I noticed when you were introducing me, Desh, the voice was sort of breaking down, so I'm not sure if it's the internet connection on my computer or on your end. So if you hear...
If this must have been my end, sorry, apologies for that.
No problem. The reason I'm mentioning that is that if my voice breaks, please do let me know so I can backtrack, because the only way for me to know it would be if you let me know. Maybe you can put it in the chat or interrupt my talk as well. All right, so this talk is about a new paradigm for accelerating scientific discovery that brings the scientific knowledge and machine learning together. And it's a work funded by multiple agencies, primarily the NSF HDS EGR program, but also DARPA, USGS, and other agencies. So let me start by saying that we are in the middle of a big data revolution. And of course, the revolution started 40 years ago, almost 4 decades ago, and it's continuing, but it's accelerating. And the momentum has become bigger in the last 10 years. And of course, it's picking up steam further, as we progress into the future. And it's fueled by the 3 technology trends. One of them is high performance computing. The computers are becoming faster. The second is the availability of very large amounts of data. That's happening because of the technologies that allow us to collect data in all walks of life and in all scientific disciplines. And advances in this field called big data, machine learning, data science, statistics, whatever you want to call it, the science of data that deals with algorithms, that science has advanced tremendously in the last few decades, and certainly with the deep learning revolution. And these 3 technology trends actually have aided each other. That is, one has fueled progress in the other and vice versa. And together they have completely upended our life, right? They have been hugely successful in commercial applications. You can you can sort of you can see the impact in the way we conduct business, interact with each other, buy products, entertain ourselves, even elect our representatives. And we're in the middle of this pandemic, and our life still goes on for the most part because of the success of this big data revolution and technology that sort of goes along with it. So this has been a tremendous success story from any perspective you can imagine. And similarly now, there is a interest in seeing if this revolution, data revolution, can be harnessed for scientific discovery. And again, and this is not a, people working in data science saying it, but it's, the push for this is coming in from all of the scientific disciplines who are seeing the big value in bringing the machine learning, the technology that has fueled so much development. Can it also help with the scientific problem? But the straightforward applications of the machine learning, data science, data mining algorithms, often called also black box algorithm, have shown disappointing results in many scientific domains. And as a result, this has sort of created some setbacks. And there are a number of reasons for these disappointing results. One of them is that these algorithms, especially the most recent state-of-the-art machine learning algorithms, they require a lot of data to be able to build complex models. And such, even though we have a lot of data in scientific domain, but of the kind that you need to build these predictive models, is the labeled data for predictive models is certainly not as frequent as one can expect in language translation and image recognition and so forth. Okay? So that has been sort of one big disappointment. That is, there are a lot of very important problems that could potentially benefit from machine learning and advances in machine learning and data science. And yet these novel algorithms, these state-of-the-art algorithms really cannot be made to function in absence of the massive amount of data they need. Okay? The second thing is the black box algorithms by their nature are unaware of the physical realities, of physical laws of the world. And as a result, they can generate results that are physically inconsistent. Okay? And that, of course, bothers the people in the scientific community, because that sort of tells them that this box hasn't really learned the real relationship, perhaps is going to fail in unseen scenario. And indeed, one of the biggest failures of these black box methods has been to be able to generalize to unseen scenarios. And the reason is that at the end of it, no matter how sophisticated these algorithms are, at the end of it, they are only computing some sort of statistical relationship in the data. And of course, these relationships are getting more and more complex, and the algorithms are getting much more sophisticated, but the algorithms are not able to see the relationship that are not already present in the data. And of course, you need a lot of data for that too. So generalizability to unseen scenario is, of course, a huge, huge concern. And the third thing is that even if my machine learning algorithm, my black box algorithm, is able to provide me the right solution, it is not able to lead to the next level of science that you need to be able to do to advance the field. So basically, the science is advanced by developing new knowledge and building on top of the previous knowledge. And when I have a black box algorithm, which is knowledge free but gives me good results, I haven't advanced the field of science the way it should be advanced. And of course, I could sort of talk about many such examples where these points can be illustrated, but I will just highlight just one, a high-level applications of black box methods to scientific domain, which is being able to predict the flu trends by simply looking at the queries that are being done by people at large. And about 7-8 years ago, Google sort of came up with this Google flu trend, the machine learning algorithm, which would simply look at the list of queries people are doing and use them to analyze them to predict the outbreak of flu, oftentimes several days or sometimes even a couple of weeks before CDC would make the announcement. So that was very exciting. But then as this program sort of got built, and then they started doing projections, and it turned out pretty soon that it started over-predicting. It became disconnected from reality. And again, the reasons, of course, are what you're sort of seeing here on this slide here. Okay, so now, so this is where we are. So basically, just to reassess the state of where we are, we have two kinds of communities, two kinds of sort of solution methods. One of them are the traditional, and then both of them, of course, in the you can sort of think of as possibilities for addressing scientific problems. And one of them is that you have a great deal of scientific theory available to you, scientific knowledge, physical knowledge, whatever you want to call it. and you build models to make predictions. And if the scientific knowledge is good enough, your predictions would be good enough. Your scientific knowledge, your models don't have to be perfect. No models are ever perfect, but they have to be good enough to make the prediction. And then you can, and then they can be, they can give you whatever exactly you need. For example, if just by having access to the Newtonian physics allows you to launch a satellite you can launch a device to travel to Mars, and then it will sort of, everything from the Newtonian physics to be able to do that. Okay? You don't need any data science algorithm to be able to do it. Okay? On the other extreme, you may have so much data that you can build models that are really, really good. And I'll bring up the example of language translation, which, of course, as a field, was one of the first important field considered in the field of AI, dating back to more than 5 decades. And about 4 decades ago, about 40 years ago, DARPA had given up on language translation because they were pouring in so much money and then things were not going anywhere. And pretty soon, of course, people started making progress as more and more data became available. But most recently, with trillions of sentences available on the web in multiple languages, now it is possible to do translation from one language to other, and really pretty high quality translation. And it's available on your PDA. You can go travel anywhere, point your phone to anything. If you have the right app, it'll give you the translation. And for the most part, this translation technology uses very little of the linguistic theory that has been built over the last many, many decades. This translation algorithm really knows nothing about the text, except that it can do a pretty good job of translation. So you have these two extremes. One is I have a lot of data and I can build good models with good predictability, even if I have no understanding of what's going on. The other extreme is I have good enough understanding of the problem to be able to make predictions of the kind that I need to make. Now, these are the two extremes that happen to be, that occur actually less frequently than you would like. In most scientific domains, you have a model of physical reality which is incomplete and approximate. And it actually has a lot of parameters. The parameters have to be sort of calibrated using observation data. And because this calibration process is very buggy and very complicated, these models don't often perform very well. Again, this thing can be sort of, you can sort of say that in almost anything of importance. You can talk about these models who predict the tracks of the hurricanes, or the climate, or the weather, or any other kind of modeling that you're doing in a scientific domain. Your models are not complete and precise enough to be able to give you the results that you need. So there is a huge urge for bringing in, of course, the machine learning technologies, but on the other hand, these pure data science models people develop are data hungry and again have all of the issues that I talked about. So given these two extremes, now there's a big push, and again, this there's a big push now in sort of going beyond the limitations of these two extremes. And let me see if I can push to the next slide. Yes. So basically, there's a big push towards building a new kinds of models, which we sort of call as theory-guided data science. That is, they are the data science models that are guided by scientific theory or scientific knowledge, and they build on the foundation of data science while taking full advantage of the domain knowledge. Now, and the idea is that this set of techniques would basically be able to leverage all of the scientific knowledge along with all of the advances that have been made in the ability to analyze data at using more and more sophisticated algorithms that the community has developed over the last many, many decades, and certainly in the more recent time. Okay? And again, we sort of have been sort of pushing this direction for bringing theory and data together. And we wrote a series of papers, going back to 2014. But more recently, about 3 years ago, we wrote this paper, Theory-Guided Data Science, a New Paradigm for Scientific Discovery from Data. And it's sort of captured the excitement and the promise of this, bringing these two things together, and how, how many different ways one could potentially try to build this paradigm, and then how people are sort of working in this direction from multiple disciplines. Okay. I should also note that the work on this topic has been referred to as knowledge-guided machine learning, science-guided, physics-aware, physics-informed. So all of these terms are actually very similar, and that different people sort of use them for different times. And one should not sort of confuse and keep them as distinct. Okay. Now, this paradigm of knowledge-guided machine learning actually is very widely applicable. There is not a single scientific domain where I have not seen a possible value for this. And actually, there is so much work in this area now in different communities and different subgroups that we just finished a survey just a few months ago, integrating physics-based modeling with machine learning. And it actually, the survey reviews about 300 papers, all published in just recently, in just last 3 or 4 years, in disciplines as diverse as material science, social science, medicine, climate science, and any domain you can think of, you'll find papers there. There are programs from the funding agencies like DARPA. There's a roadmap for AI, which is 20 years of roadmap, and it highlights, of course, this idea of bringing machine learning and scientific disciplines together. There are a series of workshops and conferences that have held. I just listed a few just in 2020 alone. So this is a very vibrant field. So the rest of my talk is going to sort of try to give you a little bit more sense of what this discipline is and what kind of questions people ask here. And I'll talk about the progress made by our group in the context of a few problems that are of interest to us. Okay, so one of the questions one could ask when you sort of say, can I bring black box data science and physical sciences together, or scientific knowledge together? The first question one could ask is, could machine learning models be powerful enough to outperform physics models given sufficient data? Okay? Now, this is a very important question to ask, because physical models can be extremely complex. If you look at the model for hydrology, models for analyzing the state of the climate system, models for tracking the hurricanes, models for building devices, models for studying the energy efficiency of buildings. They're all very, very complex models. And of course, if I took a simple data science model, let's say plain regression, obviously, there'll be many, many situations I can construct and sort of say, there's no way this kind of model would be able to replicate the behavior of a very complex physical system. Okay? So we can actually ask such a question and hope to answer it in the context of physical problems, only because of the latest advances we have made in the last decade, especially in the context of deep learning, because the modeling capability has become complex enough that you can hope to be able to match the performance or exceed the performance of some of the physical models, provided you have sufficient data. Now, this is a question that sort of needs sort of study. It sort of shows a lot of promise, and I'm going to show you, of course, the solution. I'm going to answer some of these questions in the context of an aquatic science problem. Then the second question that one could ask is, this knowledge-guided machine learning algorithm, could they produce results that are physically consistent? So remember, I mentioned that one of the biggest problems with the black box data science models is that they can produce results that are physically inconsistent, which means they don't make sense from a physical perspective. So could you teach physics to the machine learning algorithm? Could you bring physical principles inside machine learning paradigm? Okay. Second question is, can they learn with limited observation data? And of course, the idea would be that if you can teach them physics, then perhaps it will help them leverage that physics to be able to learn with much smaller amount of data. Okay? And the third thing is, could they generalize to scenarios that are not present in the data? That's very important to people, because if you can, physical models, of course, they would work no matter what kind of data you give them. Whereas machine learning models or any black box data science model can only find statistical relationships in the data that you give. So the question is, how do you take them to novel testing scenarios? And again, and the list goes on. can you find novel insights that would go beyond simply getting better prediction? Could you could the model be useful if we have no observations? This is there are a lot of situations in which you have no observation data, and of course, the data science models can only work when you have data. So all the questions sort of exist, and I'm going to try to answer them in the context of an aquatic system, which of course is of great importance to those of us who live in the Midwest. There are a lot of lakes, especially in the Midwest area, certainly Minnesota. And the USGS is responsible for monitoring the health of about 100,000 such water bodies that exist in the US, because the quality of the water and the temperature of the water determines what kind of fish can survive in these aquatic systems. They have impact on the recreation, on the water quality, and all sorts of things. So this is a very important mission-related problem, and we've been working with the USGS for the last 3 years in seeing how we can build physics-guided machine learning algorithms to greatly improve the state of the art in monitoring the systems. Okay, so I'm going to be able to, I'm going to sort of address these questions in the next 10, 15 minutes in the context of the ecosystem. And just for a reference, there is a GLM, generalized lake model. It's a physical, it's a physics-based modeling paradigm that the model, which sort of is used by USGS for basically monitoring the dynamics of these lake systems. And of course, they have many other models as well. Okay? All right, so now if I had, if I wanted to build a machine learning model for lake temperature dynamics, again, the problem here is I have I have an aquatic system, as you see here on the left corner, and I'm trying to study the temperature of the water column. What is the temperature of the water at different depth of the lake? Because that temperature sort of determines the dynamics of the lake temperature mixing, and also what kind of fish can survive in it, and what may be the quality of the water that people would use for fishing and recreation and such. And the temperature of the lake, of course, is determined by weather, the meteorological parameters, like precipitation, temperature, wind speed, humidity, and all sorts of things, weather-related things, and what may be the surroundings of the lake. And of course, the GLM, the physics model, basically takes all of them into account and looks at this weather variables on different days to be able to simulate the temperature column for the lake over a period of years. So the question is, could we do the same thing using a data science model? And of course, if I need to do that, I need the data. Of course, in this particular case, the weather drivers are available going back many decades, and for different lakes. And then for some of the lakes, not all of them, but for some of the lakes, they also have, USGS also has the observations. Especially there's a lake Mendota in Wisconsin, where their data science division is located. And that lake has a very good set of observations going back last 30 years. So there are thousands of days of observations for that lake in which they know the temperature of the lake at different depth. So one could sort of say, well, this is a data-rich situation, potentially. One could sort of ask the question, is it possible for us to build a black box data science model that could take this training data? Training data would involve drivers, weather drivers, and the observations, which is the Y true. And the black box model would make the prediction. And if the prediction and the true value differ, that becomes the training loss. And the training loss can then guide the learning of the model. So basically, my objective becomes optimizing the training loss, difference between Y prediction and Y true, plus some regularization based upon the model complexity, which is sort of the standard way of optimizing for generalization. And the challenge, of course, if you apply this in a typical situation for any aquatic system, The labels, of course, there are some lakes like Lake Ventura where the labels are plentiful, but out of the 100,000 lakes, there are more than 95% which are rarely observed. They may have only 1 or 2 observations, 1 or 2 days of observations, or no observations. So there are only a few hundred lakes for which they have observations going back more than 100 days. And of course, for Lake Ventura and a few others, they have observations going back to as many as 1,000 days, going back 30 years. So scarcity of label is a big problem, which means you can't make the models to be sufficiently complex to get good performance. And the other problem, of course, is that the standard method for assessing the generalization performance and breakdown, you might get a small amount of data, label data. You could do cross-validation. You could do all sorts of parameterization. You can find a value that for which the cross-validation gives good results. And you think you have really achieved a good generalization model. But then once you deploy it in the field, it'll have very, very poor performance. So this is one problem, labels are square. And the second thing is the variable that you're predicting, the output, can be physically consistent. So if the lake is being, the temperature of the lake, of course, changes in response to the flux of energy that's coming in and the flux of energy that's going out. The energy comes in because the sun is absorbing solar energy, and its energy is going out because a warm body would also radiate energy. So the difference between these two would either warm the lake or cool the lake. That means if I'm predicting temperature of the lake body from one day to the next, the energy difference, that means energy in and energy out, the flux of energy in and flux of energy out, difference should actually match the amount of energy lost by the lake over a period of a day. Okay? So which means energy should be conserved, and these machine learning algorithms could end up giving potentially reasonable prediction, but without honoring this law of physics. And again, there are multiple other laws. For example, the dense water happens to be heavier, and also the relationship between density and temperature. So if you make a prediction of temperature column, then you want to make sure that temperature translates to density, and density then should honor the gravity. And it's entirely possible that the machine learning algorithm may produce inconsistent results. So these are the sort of the challenges. Okay. Now the question is, could you incorporate physics inside the machine learning model? And it turns out this challenge can become an opportunity. That is, by making the objective function physics aware, that is bringing in the training loss, a component of not just the training loss between Y2 and Y prediction or the model complexity, but if you also bring in the physics-based loss, which is sort of focusing on the energy conservation or depth density consistency, you have the opportunity to produce results which could be consistent, which could at least be physically consistent. So I would call it a soft constraint, okay? But it could be very useful and very helpful in some cases. Now, one of the big advantage of introducing this physics-based constraint in the loss function, in the objective function, is that now I am able to learn even in absence of observations. And let me tell you what I mean by that, okay? Even for Lake Ventura, for which we have 30 years of data, which means we're talking about, about 4,000 days, approximately 4,000 days, I have observations only for about 1,000 of those days, okay? Of course, most other lakes, I have observations for only a few hundred days, and for some of the other lakes, I have observations for a couple of hundred days, and for most other lakes, I have observations for very, very few days, okay? But the idea is that if even on a day on which I do not have the observation, I can still compute my physics loss. So if you look at this picture here, the upper half of this picture is useful when I have the observations because I can compute the training loss, okay? But the lower half of the picture comes into action even in absence of observations, because I can always use the drivers. Drivers are the weather variables, which are available, from historical records, and then you can generate them from weather drivers. And given a weather driver, I can create the weather by prediction. If I happen to have the observations, I can compute a training loss. But if I don't, I can still compute the physics-based loss. And that physics-based loss can still regularize the construction of my model. So that's another very powerful way I can reduce the reliance on the label data. And of course, if you do this, you can build this neural network, which is LSTM, which has a state component. But the LSTM, the traditional LSTM, of course, can be built for a problem like this. If you bring in no energy component, no energy conservation component, it'll be a black box LSTM that you would run literally just by taking the weather drivers and the observations and then train them without knowing anything about the physics. Or you can add this physical component by keeping track of the energy fluxes coming in and going out and using them to compute the regularization on the changes in the temperature that are being predicted by LSTM. Okay, so basically you can have this physics guided, if you take the blue portion out here, it's a plain LSTM. If you bring in the blue part, it's the physics guided LSTM. So this is one way physics can be brought into a traditional machine learning algorithm. But this is only one way to capture the physics of the machine learning, physics of the complex model. There's a lot more physics that's inherent inside a GLM type physical model. And one way to capture all of that is, and also to overcome the data sparsity challenge, is by pre-training this model using the physics model itself. Remember, the physics model itself can create output given any driver. No matter what temperature profile you would give, no matter what weather profile you would give, it can create a sequence of temperature profiles for the lake. And you could use that data to train the machine learning model. And of course, the drawback is that your machine learning model can at best approximate the physical model, which means it cannot address the limitations of the physics model. But it could still learn a lot from the teacher, a bad teacher so in this particular case. And once you have learned enough from the bad teacher, you could perhaps use the observations to make any correction. Okay, so that's the idea. That is, if you do pre-training using a physics-based model, no matter how incomplete it is, it might bring the machine learning model close enough to the final solution that it can be modified very slightly using small number of observations. So this is a hope. Now let us see whether this hope really works or not in practice. So I'm going to show you now the results. So you have the Lake Mendota. I'm showing you the results for Lake Mendota. You sort of see here the green curve here, which is basically showing you the performance of a pure physics-based model, the GLM, state-of-the-art model used by USGS. If the model is uncalibrated, which means that the model has some standard parameters which are going to be used for this location of Lake Mendota, its error is actually more than 3 degrees RMSE. The RMSE between the observations and the predicted error is more than 3 degrees. But as you use more and more observations, 10 days worth of observations, 50 days, 100 days, up to 1,000 days, the calibration process could help you find better values of the knobs inside the model. And most physical models have these parameters that have to be calibrated. And as you calibrate those parameters using observation, the performance improves. And you can see that the performance gets closer and closer to about 1.8 degree RMSE. So it's an improvement from unobserved situation. Okay. Now let's see what happens if I apply a plain black box LSTM, no physics. Okay. This is the red curve that you see here. That is, if you give it very few observations, like 10 days worth of data, and of course on each day I have the entire water column, it has actually pretty bad error. Okay. But if I give it 50 days of data, it actually starts doing pretty good. At 100 days, it matches the traditional LSTM, and at about 1,000 days, actually exceeds the performance of the GLM. So this is very promising. This answers the very first question. That is this physical complex? Is this physical system? Can this physical system be approximated using a data science model, provided we give it enough data? And it turns out that this system, of course, can be approximated pretty well if you have lots of data. But of course, for most lakes, we don't have anywhere close to this data. The common of data we may expect maybe just a few dozen days at most in many cases. So then I talked to you about being able to bring in the physics inside the LSTM and pre-training the LSTM using a bad teacher, which is the GLM, right? And the GLM that I'm going to use as a teacher would be the one that has seen no observation at all. This is the uncalibrated GLM. And then you get this purple curve. And you can sort of see that if I learn it from the teacher which has not seen any observations, and even if I have just a couple of days of data, my performance improves to become as good as the GLM with the best possible calibration. And of course, if I give it more and more data, then the performance improves quite a bit. And if I have huge amount of data, then of course the purple and the red curve merge, which would sort of make sense. Okay, but remember, this is still one lake, and I'm taking, I'm basically training it using half of those 30 years of data and testing it on the other half. The division is, I think, more about 2/3 and 1/3. So there is basically portion of year that are used for training and portions of year that are used for testing. They're completely disjoint, but we're not going out of sample here. Okay. Now, just to see whether we can generalize to out of sample scenario, which is the most important thing, let's look at this scenario here. So here I'm just showing you the two scenarios. The left box is the training and testing are similar. So basically, the points here are coming from the previous curve. That these points belong to the case in which all three methods, the process-based method, the deep learning method, and process-guided deep learning method, all of them are shown 500 days of observations. So you can sort of see that the process-guided machine learning method does better than the deep learning method, which does better than the process-based method. So these are the results that you already have seen on the previous slide. On the right side is what you're seeing, something is extremely interesting. Here, for the entire set of data that we had, we hid the observations from summer from every one of these paradigms. That means the process-based method was not calibrated. When it was calibrated using spring, fall, and winter, but not in summer. The deep learning method was not shown any of the summer data, and it was used, everything else was used for training. And the same thing for process-guided machine learning. That is, it was trained by a process-guided method, which had seen no data, and then it was refined only using spring, fall, and winter, not in summer. And when you do that, you can see that the process-guided deep learning method had a very small reduction in error. The process-based method actually had a pretty big reduction in method, which is not surprising because the parameters have to be calibrated, and they got calibrated to be suitable for spring and fall and winter. And the pink one, the RNN, of course, dropped like a rock, which is not a surprise, because if the machine learning hasn't seen the relationship in summer, it has no way of predicting it. So this gives you the hope that yes, this paradigm can actually go out of sample. Okay. And this slide simply shows that yes, indeed, these physics-guided machine learning algorithms can actually match the flux in and flux out, and difference between the flux in and flux out of energy versus the energy change in the system. So the last curve here is the GLM, which is the physics model, which of course the curve would match. And the first curve here is the black box machine learning model, and you can sort of see the energy balance is not matching. You can see the two curves, and the middle one, of course, the match pretty good, even though it's a soft constraint. Then, of course, I showed you results on one lake. USGS monitors, hundreds of thousands of them. Here, this picture is showing you that the next experiment we did was the 69 lakes, for which they had a couple of hundred days worth of data. And again, the results are very similar. That is, the pure process-based, the process-guided deep learning actually does significantly better than pure process-based model in large variety of them. And then the next, I'm running out of time, so I'm just going to sort of show here that this set of slides are supposed to show that if I'm pre-training my machine learning model using a process model, the question is how good the process model has to be for pre-training. So first, of course, I used the process model that had no observation data, which means it was uncalibrated. But then the process model still knew about the geometry of the lake. That is, what is the depth profile? How clear the lake might be, what the climatic conditions may be around the lake. So there are all these different parameters that one sort of happens to know, for example, about something like Lake Mendota. But the question is, what if my depth profile was not correct? What if I'm looking at a lake far away in a far away place, and I don't have a good data about its clarity or climate conditions or something? How well would my pre-training process survive that thing? And then basically for the lake profile, if you see these 4 profiles here, the last profile is the one that corresponds to the actual profile of Lake Mendota. The other three profiles are are shown here to show that what if I train using not this profile, which is in the rightmost corner, but the one which looks like a box, or the one that looks like a triangle, or the one that looks like a wine cup. And of course, if you use the Mendota profile, the teacher would give you better training. And what this table, and I'm not going to go into the details, but one could sort of read the paper, shows is that even if you went to something like a box or a triangle, your performance is actually not that bad. Just a few observations, just maybe not a very small number, but just small, still a very relatively small number of observations would let you train the model good enough. Of course, if you go to extreme like a martini, then it becomes bad. So the idea is that you don't have to know a whole lot about the lake geometry to be able to use it for pre-training. And the same thing applies to the notions of clarity and other things as well. And then I'm just going to mention one last thing here just for a minute. That is, what if I'm looking at a lake system for which there is no observation data? Of the 100,000 lakes that USGS is supposed to monitor, there are about 90,000 lakes for which there is a zero observation data. Okay? And of course, they can create observation data by sending people, by sending sensors. It costs them thousands of dollars to collect some observations. And they can certainly, if you build a system, they can certainly use it to verify. Okay? But the idea would be that how could this paradigm help in a situation when there is absolutely no observation data, which of course is a very difficult problem. But it turns out that even in cases like these, you could build transfer learning paradigms in which you could take the few hundred lake systems for which there's a lot of data and figure out how, given this very well observed system, figure out using other properties of the lake, other physical parameters of the lake to figure out whether one lake could borrow a model from another lake. Of course, the borrowed model won't be as good if you had built the model for itself, knowing all of its eventualities. So, but this paradigm actually has worked very well. I'm showing the results here. Meta model built using 180 lakes, which had at least 100 observations, and then transferred over to a very large number of lakes. Basically, and of course, to be able to do the testing, I have to have at least some data about the lake. So they found about 2,000 lakes for which they had at least 10 days of data. So we were able to actually assess whether this thing would work. So basically, we built this meta model using only a couple of hundred lakes, and then we used it to show that for the other couple of thousand lakes for which we never used them, we just used this meta model to do the transfer of modeling of the lake, of the PGDL model. And then we were able to get actually very good performance. So you see the blue curve is what you would do if you use the uncalibrated physical model. The RMSE gets pretty, very high. And if I do the transfer modeling, I can actually go to much smaller errors for the most part, for most of the lakes. Okay. Now, the paradigm that I talked about sort of grew out of a series of work that we have done, and again, this expedition project on understanding climate change, a data-driven approach, in which we basically work with a lot of environmental problems and we build data science solutions for them. And one of the things, of course, that came out in that one was that these data science approaches have to be cognizant of the underlying physics, and which sort of led to this hybrid physics data models, or you call them physics-guided models. And that's sort of what I sort of gave you about. So let me conclude here with just a few comments that this knowledge-guided machine learning paradigm offers a promising approach for addressing limitations of pure machine learning, of pure data science, and pure process-guided approaches. But there's a lot of work that's needed to be done in this direction. And I showed you a very simple physical system, very important, but very important, simple physical system for which we build this process-guided data science model. But many systems are far more complex. For example, there are lakes, but there are lakes connected by rivers or the river streams, and they impact each other. There are hydrological systems in which you have river basins that are impacted by not only rainfall and temperature in the basin, but also what is being grown in those basins, what may be the groundwater, what may be the quality of soil. So there are many complex components of a physical system, we need to figure out how do we bring them inside a model learning and model architecture framework. That is, we have built these architectures in sort of the architecture sort of that we're using right now are not designed for specific physical problems that we are solving. And there's a lot of opportunity here to sort of bring that knowledge back into it. And in the physical science domain, people build these physical models, and they can also be modified on the fly using real-time observations data. It's called the data simulation. And again, this concept of how do you bring this data simulation into these process-guided machine learning setting is yet to be discovered. So with that, I'm going to stop. Here are some of the papers. I have given my slide to the hosts here, and then they should be able to share them with you. And I just want to sort of point out that this work, a part of this work is funded by the Harnessing Data Resolution program of the NSF. And then we held this workshop for this project just about a month ago. And it was a 3-day workshop, had about 40 different speakers. And all of the talks are recorded. And there were about more than 1,000 people registered from all over the world. And these talks, of course, are available for anyone to see. So my talk gave you a very high-level overview of this topic. But if you go to this workshop webpage, you will have the opportunity to listen to several dozen people talk on very specific cases and advances in this area. So with that, I'm going to stop and thank you all, and I'll be happy to take any questions.
Thank you, Vipin. We do have some questions here. So Drew, would you like to go ahead and speak your question, or do you want to type?
I think typing would probably cost more time here. I'll just be quick. Thank you, Dr. Kumar, for a very interesting talk. So I'm very interested in the pre-training mechanism you described. So I just want to make sure I understand it precisely. So by pre-training, you mean that I'm trying to guess what exactly you do there. So you use the physics laws to generate simulated data, use that to train the neural network, to initialize the neural network. Is that correct? Or is there?
Yes, yeah. So let me go back. So basically, for any of these problems in which people are trying to solve in physical sciences, they already have a physical model that they're using. So for example, for the lake temperature monitoring, they have GLM. For monitoring the temperature and quality of water that flows through the river streams in the United States, USGS has built a model called SNTEMP, for example, right? There are lots of models that people have built in hydrology for assessing whether a certain area is going to get flooded in response to rain or not, right? So all of these models already exist. Now, these models, of course, are not able to predict as well as they would like them to predict. So the question here is, rather than ignoring the knowledge inherent inside those models, what if we use the data generated by them to pre-train our machine learning algorithm?
Sure.
With the hope that this machine learning algorithm would not need a lot of data to actually, a lot of observation data to actually get to the final result.
Sure, yeah.
Okay.
It makes great sense. This is actually consistent with what the deep learning community is working on these days. So the other question, quick follow-up on this line of thinking is, so this is the technique. Mm-hmm. Then going back to the sort of the fundamental principle underlying this idea, I mean, this way of doing it actually hints at one way of doing science, which is, okay, we have some basic understanding to start with, then you use data to fine-tune your understanding.
Yes.
So this is fine, but I want to sort of carefully challenge this perspective in the sense that this is not exactly scientific discovery. We are not really discovering anything that's particularly new. We're using observational data to sort of fine-tune things we kind of already know.
Perfect. Absolutely, absolutely. So this is a component. This is a component in the whole system. Okay. So let me say two things here. Number one, this is actually a very important building block. I actually showed this building block in the context of seeing whether I can build a better predictive model, okay? A better predictive model that requires less data and maybe produce results that are physically consistent. But a lot of people are using just this emulation. They call it using machine learning to emulate a physical model in many other contexts. For example, parameterization and more efficient emulation of systems. But let's not worry about that. But let me hit upon the point that you're just talking about. That is, does it have any, in addition to giving better predictive power, which of course you saw, right? No, here, does it have any hope of giving me any more insights? I think that's your question, right? Is that correct?
Right, that's right.
Okay, so now let me go over a slide that I skipped. I thought I won't have time for it. Okay, so look at this slide here. Let me see. Yes, this one. Right. Okay. So you saw that this physics-guided RNN is actually giving a very good result compared to a black box RNN, which is of course not surprising. This is, I'm showing you RMSE spread across depth, like how much error is being made at the surface versus deeper area. So you can sort of see the physics-guided machinery is actually giving much lower error at the depth, at the deeper level of the tree, of the lake, versus the surface. Okay. Now these are both machine learning models. Now look at the GLM. I'm going to show you in the next slide the result of the GLM. The curves look completely different here because I had to change the scale. In the left one, the maximum error you're seeing is 2. On the right side, you're seeing maximum error to be seeing is 5. So what you're seeing here is the GLM, the physical model, actually is making massive amount of error in the middle. Okay, so so what you're seeing here is the physics-guided RNN is actually learning from the GLM. The red curve is learning from the green curve, which is the uncalibrated physical model. And yet, after doing the observation, is actually getting the results almost perfect in the middle. So to the USGS people, what this was sort of telling them was that there are certain processes that are involved in the dynamics at the middle layer that are probably not being represented better in the GLM. So this is what I meant by also being able to extract some understanding, because if I'm able to train from a teacher and do better than it by using a few observations, then it helps me point to some inadequacies of the physical model. Now we are taking, of course, a very similar approach in hydrological systems, which are of course far more complex than the model that you're looking at here. So hopefully this answers part of your question.
Oh, thank you. Thank you. This is a great example.
Thank you, Vipin. Next question is from Dr. Julie Dickerson. Julie, if you could use the microphone if you want.
I had questions when you were talking about incorporating novel information, and you answered some of them, but have you compared to what an expert in the area would have come up with versus just the mathematical models?
Okay, are you talking about the physics-based laws or something else?
Yeah, so somebody came up with these models, and so there's already an existing physical-based model. So has there ever been efforts to talk to the people who actually came up with this model and say, well, what would you have anticipated would have happened in this case? So we can have a more fair comparison. How did these models compare with what somebody who's been working with in the area for a very long time would come up with?
So, okay, so again, I don't know if I am answering that here in the slide, because this is the slide that shows you the state of the art. The green curve is the state of the art. This is what USGS uses for modeling the lakes around the US. This is the operational system. And of course, they will not use this RNN, the orange line, because orange line would work only for Lake Mendota, for which they have a lot of data. Okay? And with orange line, they cannot trust it, because if it works for the last 30 years, there is no guarantee it's going to work in scenarios of weather that change dramatically. Okay? Now the orange system here, the purple line here, is showing you, of course, the paradigm that I talked about and outperforming it. USGS is planning to sort of basically making a wholesale change to these kind of models as a result of this. So this is the case in which there is a mission agency whose job is to monitor these lake systems, and they're sort of seeing, yes, this kind of research would help them move in a completely new direction.
Vipin, do you have time for one quick question?
Sure, I can take maybe one question.
So next question is from Dr. Namrata Vaswani. Namrata, if you could, please.
Sure. Yeah, sure. Can you hear me?
Yes, I can hear you very well.
Hi, Vipin. Nice talk. I saw some of this the second time. And I am always a fan of physics-based approaches. A lot of my work also does that. But my question is, why are you combining the physics model with a deep learning or with a deep neural network, as against combining your physics-based model with 100,000 possible existing approaches? For example, you could optimize a weighted sum of, let's say, the data likelihood term plus the prior term, or you could come up with a real-time tracking approach depending on the problem at hand. Because the deep learning model is, again, a prior that you're putting, right? You're assuming this will be my model based on past data. You're not updating it on the fly.
Precisely. Okay. Very, very good question. So actually, my answer to that would be that these deep learning models actually already are on the path of taking the basic data science models and adding more and more physics to it. So to me, the LSTM is effectively bringing in the time component, when actually the RNN are bringing the time component. You have a plain RNN, they don't perform as well. LSTM is bringing a much better control on the state. So for example, I'll give you an example here. If I use the plain neural network or any kind of regression techniques or any other machine learning technique, it does horribly in this case, because you can see a 40-degree day in January in Minnesota, and you can also see a 40-degree day in July. But the lake status would be completely different in both in January and July for the same data temperature, because there's a state that comes in. In January, our lakes are frozen. The upper layer of the lake is going to be frozen. In July, of course, it's very warm. So you cannot have the temperature profile in January and July to be the same, given the same given the same weather conditions. So there has to be a notion of state that has to be brought in. And if there are other data science models that can bring in the state, but we have, for example, if you try to bring in things like ARIMA models, they're not powerful enough to be able to bring in the nonlinear aspect of the state. So one thing I can talk about is that if you actually use the standard statistical methods for time series analysis, they actually perform very poorly for problems like these.
Okay, but do you have comparisons with
Yes, yeah. I didn't show them here, but we actually constantly try many other things in addition to that. Actually, now we're looking at hydraulical systems, and building black box model the way I just talked about doesn't work very well there. We have to go more deeply inside the structure of the physical system and build models for different components. So for example, if I'm trying to figure out the hydrological flows, I have to figure out in a place like Minnesota, how much snow has fallen, how moist the soil is, and what may be on the ground in terms of crops, which may be causing a lot of evapotranspiration. You're in Iowa. If there's a corn in the field, it's just basically pumping water out of the ground into the sky as the corn grows. So there are a lot of other processes happening, and unless you model them properly, your machine learning model framework has no hope. So basically, I can build a machine learning model, but its design has to be informed by the overall physical structure of the system that you're trying to emulate.
Sure.
The more you know about it, the better it is. And that happens as a result of sort of dialogue between the data scientist and the physical scientist.
Good. Okay, I'll just take the questions offline. Yeah, I guess we're out of time.
Yeah, thank you very much, Vipin, for your time. I want to be sensitive to your next meeting and appreciative of all of your taking the time to talk with us. Thank you again. You get a chance to come and visit with us in person and give another speech. Appreciate that.
Very good. Thank you. Bye-bye.
Thanks, everybody, and thank you. This concludes the TADS seminar for today.